So far, we've talked about tokenization, which again converts strings into sequences of integers called tokens that we can give to a computer. We'll end this lecture by seeing how we can build a simple classifier over tokenized text. And here we'll be working with a classic task of sentiment classification, where we're given a movie review, and we want to classify this movie review as positive or negative sentiment. And this is a classic machine learning problem where we're given some data, i.e. the movie review and the label, and we want to learn this function from data. Now, the starting point for any natural language application is to use the tokenizer that you've learned, in the case that we've been talking about in this lecture, byte-pair encoding tokenization, to convert strings into sequences of integers. So each sentence gets transformed into a sequence of integers, where each integer represents a token. Now, suppose we want to train a basic linear classifier over this. One issue arises from the fact that in language, the inputs have variable length. But many classic machine learning models, like logistic classifiers or tree-based classifiers, expect fixed dimensional inputs. So this motivates what's called a bag-of-word representation. So in bag-of-words representations, you represent each sentence or each document or a variable length input as a vector with v dimensions, where v is the token vocabulary size. So in particular, you might have a sequence like 20, 40, 51, 1, 1, 10, so on and so forth. Again, this is the token representation of a sentence. For these variable length sequences, you represent it as a vector of dimension v, where an element of this vector is 1 if the token corresponding to that dimension appears in the example. Otherwise, it's 0. So for example, in the first sentence that we have here, at the position 1, 1, 10, this element is 1 because the token 1, 1, 10 appears in the sentence. Likewise, at position 8, 8, 3, 1, this token appears in the sentence, so it's 1. All the other dimensions corresponding to tokens that don't appear in the sentence are given the value 0. And this means that we've now represented a variable length sequence as a fixed dimensional vector of zeros and ones, where the size of this vector is v, where v is your token vocabulary. Great, so now we have a fixed dimensional representation of your input, and we can learn a classifier over this input. And this is a classic machine learning problem now. So in this case, we're given a training set of n examples where we've now used tokenization along with this bag-of-word representation to represent each input as a vector xi that is of dimension v. And then in the training set, we're also given labels yi, that's corresponding to 0 and 1, which correspond to positive or negative sentiment. Now, given this data set, we can train a simple linear classifier, a logistic regression classifier over this, where the probability of the review being of positive sentiment, i.e. y being 1, is given by a sigmoid function over some linear function of x. So in particular, we have the probability that label is y, given the input being x, is the sigmoid function over a number that is given by applying a linear function or linear vector wt, having that dot producted with the input x, plus some bias term. This is also called a log linear model in the literature. So we've now specified how we can use w and b to obtain a distribution over labels 0 and 1 given the input x. How do we actually learn w and b? One way to do this is through maximum likelihood estimation. This finds w and b such that they maximize the probability of your training data. What is the probability of your training data? If you assume independence, this is given by multiplying the probability of each label or each data point. And we notice that we can turn the multiplication sign into a summation by applying the log function. Because the logarithmic function is monotonic, this does not change the optimization problem. So now we can use the fact that we've defined as a modeler the probability of the labels being y given x to be a logistic function. And if you write out what this looks like, you obtain an expression as follows. So given the objective, how do we actually find the optimal W and B? It turns out there's no closed form solution for W and B, but iterative optimization methods such as gradient descent work well in practice. So first, we turn the previous objective, which was a maximization problem, into a minimization problem by multiplying the log likelihood by -1. So we get small L of I, which is the negative log likelihood of that data point. And if you derive the gradient with respect to this negative log likelihood for a data point, you get an expression as follows. And of course, in gradient descent, you update your model weights W and the bias term B by subtracting the gradient multiplied by learning rate eta. And it's instructive to look at sort of intuitively what this is doing. So the intuition here is that here y hat is the prediction. So if the prediction was close to the actual, so if the difference between y hat and y is close to 0, you actually don't change the weights much. And this makes sense, right? Because your model was getting that data point correct. But if you were pretty far away from the actual label yi, then you take a gradient step such that it points in the same direction as x, so that the next time you see this data point, you will more likely classify it to be correct. So that was in the case of binary labels, where the input is either 0 or 1. It's straightforward to extend this to classification over k classes. In this case, we might have k labels, so 1, 2, until k. And we generalize this by now having weights W associated with each possible label. So to get a score, what's called a logit for a class k, you apply this wk, you dot product this with your input xi, and you apply the bias term bk. Now, zk is not a probability distribution, but to do maximum likelihood learning, you need to obtain a probability distribution over labels, and you can do this by applying what's called a softmax function. There are many other ways to get a probability distribution over labels given zk, but softmax is often used in practice. And the softmax function turns these scores zk into probabilities by exponentiating and then normalizing over all possible labels. And you can apply the same approach where now you still do maximum likelihood learning, or you minimize the negative log likelihood of your training set, and gradient-based optimization will work well in practice in this case as well. So we now have an objective that we want to optimize, i.e. the negative log likelihood of your training set. Now it turns out, especially in text, because your input is very high dimensional, your model can easily overfit. So your input, it can be a v-dimensional vector where v can be in the order of tens, if not hundreds of thousands, and that means you might do very well on your training set. So you might easily optimize the negative log likelihood on your training set, but this won't generalize to new data. So often one adds what's called a regularization term, which prevents the weights from becoming too large. There are many ways to do this. A popular approach is called L2 regularization, wherein you add an L2 penalty of your weight vector to the optimization objective. And this prevents the weights from becoming too large, and this mitigates against overfitting to your training set. So that was a simple example of logistic regression. But now, as I mentioned before, because we've now have a fixed dimensional representation of your text, so we use the tokenization function along with the bag of word representations to represent a variable length sequence of integers as a fixed dimensional vector. You can apply other types of models on this. So perceptron models, support vector machines, and nonlinear models such as tree-based models or nearest neighbors can also be applied to this representation. But it's also worth being thoughtful about whether some of these models may be appropriate or not for the application of interest. So for example, we should remember that these bag of word representations are quite sparse. In particular, we might have a vector of dimension 100,000, but only a few of them might have non-zero values. And we should be careful about whether methods, such as tree-based models, might be appropriate for these types of representations.